Okay, welcome to Chapter 9. So let's talk a little bit about gases. All right. If you'll recall, a long time ago we talked about, back in Chapter 1, I think, we talked about solids, liquids, and gases. And we said that solids have a definite shape and a definite volume. Liquids have an indefinite shape but a definite volume, and gases have an indefinite shape and an indefinite volume. And I told you just remember that and we would discuss all this at a later time. Well, here we are. So let's go back and let's talk a little bit about that and why those things are the way they are. So there are three main states of matter: your solids and liquids and gases. Of course, you've got your solids. So that would be things like, ice and iron and things like that. So what makes a solid anyway? Well, solids, as we had discussed before, have a definite shape and a definite volume. They don't take the shape of the container they're in. They just pretty much are, what they are. If it's a cube, it's a cube. Doesn't matter what you put it in. They take up a certain amount of volume, and that's just what they do. There. Solids are also generally incompressible. You can take a cube of copper and squeeze on it all you want. It's not going to get any smaller, really. It's just going to stay pretty much the same. You might say, well, but I can squeeze a cork. Well, but are you really squeezing the cork? What you're doing is you're squeezing the air in the holes inside the cork when you do that. So, yeah, solids are generally incompressible. So, why? Why do solids have a definite shape and a definite volume? Why are they generally incompressible? Well, let me draw you a conceptual model of what a solid looks like. In a solid, what you have is your molecules, your atoms, are arranged in a very highly ordered structure. Something like this, a crystal structure of some sort. All right? Now, why do solids have a definite shape and a definite volume? Well, if I want to know what's happening with this little guy right here, these little guys are influencing them, see, because they're all being attracted to each other because they're so close to each other. And so there's just not a lot of freedom of movement in a solid. About the only thing that a solid particle can do is it can vibrate. And that's pretty much it. That's the only freedom of movement a particle has in a solid. And so since there's no freedom of movement, it's going to maintain a definite shape. Okay? And it's also going to maintain a definite volume. Everything's kind of, locked in, so to speak. All right? And that's what kind of gives it those properties. Solids are generally incompressible because if you want to compress something, you got to be able to move the atoms closer together. And so what that means is you got to have some empty space. Well, do you see any empty space in here? No, it's all your little molecules are kind of packed in there like sardines in a can. They're just kind of stuck in there. There's just really no more room to squish them together closer. And so solids are generally incompressible. Of your three states of matter, solids are probably the second easiest to treat theoretically, or second hardest, whichever way you want to look at it. The nifty thing about a solid particle is it's not going anywhere. It's pretty much stuck where it is. And so that makes it fairly easy to treat theoretically. The bad thing about trying to theoretically model a solid is if I want to know what's going on with this molecule right here, I have to know what's going on with this molecule and this molecule and this molecule, because all these other molecules influence this molecule. It's kind of like your friends. Where are you going to lunch? Well, maybe you're going to Taco Villa. Why are you going to Taco Villa? Did you want to go to Taco Villa? Well, you probably didn't care, but it probably wasn't your first choice. But, your friends just really want to go to Taco Villa. So if your friends want to go to Taco Villa, I guess you're going to Taco Villa. Well, it's kind of the same thing here. If I want to know what's happening with this particle right here, I have to take into account all these other particles because they're really close by and they affect it. And so essentially in physics we call that a many-body problem, which I think we've talked about that before. It's just impossible to solve and very hard to kind of theoretically model. And so that's the problem there. So, and what it ends up being, as I said, of your three states of matter, they're probably the second hardest to treat because of that. All right? Okay, well, if I take a solid and I heat it up, what do I change it into? Well, I change it into a liquid. So what makes a liquid a liquid? Well, liquids have an indefinite shape. In other words, they take the shape of whatever container they're in. If I had, say, for example, a beaker, water in a beaker, it'll take the shape of the beaker. I pour it into an Erlenmeyer flask. It takes the shape of the flask. But they have a definite volume. So if I have, say, 500 milliliters of water in a beaker, and I pour it into a flask, it's still going to take up 500 milliliters, definite volume, but it'll change its shape. All right. Liquids also are generally incompressible. In fact, there's an entire field of engineering that relies on the fact that a liquid is incompressible, and that's called hydraulics. This is how a hydraulic jack works. You push on a small piston over here with a liquid in it. That force is transferred over here to a large piston, and maybe that piston goes up if you're at the car mechanic, and your car's going up on a lift or something like that, and it kind of holds it up that way. And that's hydraulics. And hydraulic jacks work on the principle that that liquid is incompressible in there. So any force you transfer to the liquid gets transferred somewhere else. Okay? So why? Why do they have an indefinite shape but a definite volume? Why are they incompressible? Well, this is kind of a conceptual model of what a liquid looks like. In a liquid, your particles are still really close together, kind of like they were in the solid. But now they're a little bit disordered. The structure is not quite as neat and perfect. It's broken up. I kind of like to think of it as kind of like a plate of spaghetti. You've got some spaghetti molecules, attached to other spaghetti molecules in a strand, and they belong to the same strand. But the two strands, the strands that are in your spaghetti bowl, aren't necessarily connected. Well, that's kind of a rough analogy of kind of what a liquid looks like. You have some molecules that belong to a glob, and other molecules that belong to a different glob. All right. Of your three states of matter, the hardest one to treat theoretically is the liquid. All right. Because if I want to know what's happening to, say, this molecule right here, I have to know what's happening to all the molecules in the glob, because that's going to influence this molecule right here. Not only that, I've got neighboring globs over here which are influencing this glob, so I've got to know that as well. And then on top of that, sometimes these molecules just trade globs. It'll be in this glob over here, and then it'll move to a glob over there. So you got all sorts of interchange going on, and it's just a mess. And so of the three states of matter, liquids are probably the hardest to treat theoretically, which is kind of ironic because most of the chemistry we do is in what form? Well, it's in water, so it's in the liquid form. So the state of matter we use the most in the chemistry lab is the one we actually theoretically understand the least. All right? Now, why do liquids have an indefinite shape but still a definite volume? Well, because in a liquid, you have a little more freedom of movement. The molecules are a little bit more free. Okay? And so they're free enough now that they can start changing shape. All right, but they're not free enough that they can still change volume. All right, because they're still fairly tightly bound together, and that's kind of why liquids are the way they are. All right, why are they incompressible? Well, they're incompressible because although I have a little bit less order here, do you see a lot of empty space in there? No, so it's kind of like our plate of spaghetti. There's not a lot of empty air in a plate of spaghetti because those strands are all lying kind of on top of each other there. Not saying these are in strands, but it's the best analogy I could come up with. At 9:39 at night, which is when I'm doing this video, and so therefore they're still incompressible, and that's why liquids are incompressible. In a liquid particle can do two things. It can vibrate, sit there and vibrate just like a solid particle can. But liquids also have rotational energy as well. So it can sit there and it can kind of rotate. So solids only vibrate because they're too tightly held together. Liquids vibrate, but they also have rotational energy because of that more freedom of movement. And that's what gives them the indefinite shape. All right. Now what happens when I heat up a liquid? Well, it changes into a gas, right? So what are some properties of gases? Well, gases have an indefinite shape and an indefinite volume. In other words, they take up the shape of whatever container I put them in and expand until they fill it up. And they have an indefinite volume. They expand until they fill it up. So an indefinite shape and an indefinite volume. Whatever the shape and the volume of the container is, that's what the gas is going to fill. Now, unlike liquids and solids, gases are compressible. You can take a gas and you can squeeze it, and you can take it down to a smaller size. All right, and that's different. All right, so why? Well, here is kind of a conceptual model of a gas. And so a great two-dimensional example would be like a pool table. You ever play pool? Okay, so imagine you're right there. You're about to do the break. So you got your balls in the triangle up there, and you got your cue stick, and you're ready to break. And so you slam it pretty hard, and then what's happening? We got balls flying all over the place, right? Balls are just clacking around, and when the one ball hits the 7 ball, does it stick to the 7 ball? No, they bounce off and they go off in opposite directions, right? Okay, that's called an elastic collision in physics. An elastic collision is when you have a collision and your two things still maintain their energy, and they kind of go off in different directions. Think bumper cars, for example. Inelastic collisions are when two things crash together, but they stick, or you lose energy, they deform. Think a real car wreck. You have two cars that hit each other going 60 miles per hour apiece. They don't go 60 miles per hour in the opposite direction. They go to zero really, really, really fast. And all that energy goes into deforming the metal and deforming you too if you're not wearing your seatbelt. That energy's got to be dissipated somehow. But yeah, that's called an inelastic collision. You have loss of energy when you have it. Well, we know that gases undergo elastic collisions. All right, and this is the reason why. Let's say, for example, you've got a balloon. So you got all these little helium atoms bouncing around all over the place. Well, if they're hitting each other all the time and bouncing off, if the collisions were inelastic, then each time they would hit each other, they would lose energy. And so what would happen is they would lose more and more and more energy, and pretty soon you'd find all the helium atoms just sitting there in the bottom of the balloon because they've lost all their energy. Well, we know that the molecules never slow down. Now it deflates, but that's because it's actually leaking through the rubber, the pores in the rubber, not because it's losing energy. And it would stay, if you had that perfectly, kept in there and it didn't leak out, then yeah, that thing would stay going forever. All right. So therefore, the collisions must be elastic. So think of a pool table, and think of the balls as the little gas molecules, and think of the pool table itself as kind of the container. And then imagine a break where it never ended. In other words, there was no friction on the felt or anything, and those balls just bounced around forever. That's kind of an idea of what a gas looks like. Okay? So see, I've got these molecules. They're traveling in a certain direction, and they'll keep traveling in that same direction until they hit each other. If they hit each other, they bounce off each other with no loss of energy. Here's a molecule that hits the cushion. What happens when it hits the cushion? Does the pool ball stick to the cushion when it hits the cushion? Well, no. The pool ball bounces off and heads off in a different direction, right? Well, again, think of this as like a balloon. Okay, and these are helium atoms these are molecules I've drawn here for you because it works with molecules too. So imagine that gas molecule or atom, in the case of helium, hits the wall of that balloon. Well, it doesn't stick to the balloon, it bounces off the wall of the balloon. All right. Now, when it bounces off the wall of the balloon, it exerts a tiny amount of force on that cushion. Okay, and then rebounds off and heads in a different direction. Do you think it's a lot of force? Well, probably not. It's a really tiny molecule, and so therefore, it's not much of a punch there because there's just not a lot of mass there, right? But let's say I had 6.022 times 10 to the 23rd molecules of helium, atoms of helium hitting the wall of the balloon. That would be 1 mole of helium, which is about 4 grams. Okay? That's a lot of molecules. It's not much force per molecule, but do you think it adds up? It does add up. All right. What do we call that up here in our world? We call that pressure. And that's what gas pressure is. It's billions and trillions, and actually probably much, much more molecules hitting the walls of the container all at once. And what that force does, it's a force. It's what pressure is. It's actually a force applied over a certain area, and it adds up. Okay, and it adds up to something that we can actually measure up here in our world, and we call that gas pressure. All right, talk about that a little bit more here in a minute. Okay, now if you're more of a three-dimensional minded person, another thing you could imagine here is a racquetball court. Do you ever play racquetball? So, you hit that racquetball and it starts bouncing off walls, bounces off this wall, bounces off that wall, bounces off the floor, bounces off that wall over there, just bouncing around all over the place. Well, imagine a racquetball court, and then imagine like 3 racquetballs in that racquetball court going about 1,000 miles an hour. That's a good conceptual model of what a gas looks like. Okay, very few molecules, low density here. But yeah, lots of empty space in there. But yeah, they're moving pretty fast. They're just very, very tiny. All right. Now, why? What does this explain? Well, it explains a whole lot of things. What I've just done is I've just given you something called the kinetic molecular theory of what a gas looks like, and we'll talk more about this, the kinetic molecular model here a little bit later, I guess, in the chapter. But why do gases have an indefinite shape, and why do they have an indefinite volume? Well, gases are probably, of the 3 states of matter, they're the easiest to treat theoretically. Okay? Because if I want to know what's happening this molecule right here, these molecules are far enough from each other, I can neglect the interaction here. This molecule pretty much acts independently from the rest of these molecules. So again, back to our little pool table example. So I've got my 1 ball and it's flying down the table, bouncing around everywhere. If it goes by the 7 ball, is it attracted to the 7 ball? Does it change its path? Well, assuming very negligible gravitational forces. No, 1 ball's going this way, the 7 ball's going that way. The only way the 7 ball can affect the 1 ball is if they actually collide, and then of course they bounce off each other and head off in opposite directions. But that 1 ball is just going to keep going whichever way it's going, forever, unless it hits something. All right. Well, it's the same way with gas molecules. I can look at this particular gas molecule and I can ignore, 95% of the time, the attraction between these other gas molecules because they're so far away, see? And so therefore, gas molecules are actually the easiest to treat theoretically, which is why we're talking about them first. And that's why the title of the chapter is Gases. Later on in the next chapter, we'll talk about liquids and solids and theoretically how those work. But we're going to start with gases because if you're going to start with something, you might as well start with the easiest thing, right? So that's where we're going. Why are gases compressible? Well, look at my little model here. How much of this entire container is taken up by the gas molecules? Well, very little. See, there's a lot of empty space there. It's like my racquetball court with 3 racquetballs in it bouncing around. So I can compress a gas because there's lots of empty space in between, and so I can squish them together a lot easier. See? And so gases are compressible, whereas liquids and solids aren't. All right? In a gas molecule can actually do 3 things. A gas molecule has more what we call degrees of freedom. In other words, what it can do is it can sit there and vibrate like a solid and a liquid. It can rotate just like a liquid, but you also have what we call translational motion. Translational means moving from one place to another. Okay? So gas molecules have 3 types of energy: vibrational, rotational, and translational. All right? But here's the thing. The amount of energy tied up in a gas molecule is actually mostly translational. So to a first approximation, or a second or even third, what I can do is I can ignore the vibrational energy, I can ignore the rotational energy, and I can just concentrate on the translational energy of a gas molecule. And that's pretty much going to tell me the overall energy of the molecule. And that makes things nice and simple. Because remember, there's two types of energy. There's kinetic energy, there's potential energy. Well, if I've got a molecule moving from here to here, what type of energy is that? Well, that's kinetic energy, see? And so, yeah, the equation for kinetic energy for a particle is 1/2 times the mass times the velocity squared. It's like a tiny block of wood sliding down an inclined plane. Physicists just love they love blocks of wood sliding down inclined planes. I don't know why. They just really love to slide a block of wood down an inclined plane for some reason. But really, a gas molecule, all it is just a very, very tiny block of wood sliding down an inclined plane. See, whether you're talking about gas molecules, whether you're talking about blocks of wood, whether you're talking about planets, 1/2 times mass times velocity squared. Those equations in physics apply everywhere. And so therefore, you can apply those same equations to gases, and that makes gases really easy to treat theoretically. Make sense? So that's where we're going to start. We're going to talk about gases. And then in the next chapter, we'll talk about some things about liquids and solids you probably need to know. But that's probably going to be next semester. So that's, I guess that's good. Let's talk a little bit about something called the ideal gas law. So I've got a gas here. I got to do some chemistry here. Got to do some experimenting. So what are some things that I can measure about a gas? Well, one thing you can measure about a gas is its volume, how much space it takes up. Okay, lots of units I can use to measure volume. I could use liters. I've been using liters for quite a while in this course. I could use cubic centimeters here, as a gas. I could use cubic meters. I mean, just tons of units here I can use for volume. All right. Another thing that I can measure is I can measure its temperature. All right, and we had 3 different units for temperature. We had degrees Celsius, we had degrees Fahrenheit, and we had Kelvin. All right, do you remember a long time ago I said usually you can use any one. Most of the time we use Celsius, but there's going to come a day in here where you have to use Kelvin. If you don't use Kelvin, you will get the problem wrong. Do you remember I told you that a long time ago? That would be today. Anytime you see temperature in chapter 9, you've got to change it to Kelvin. If you don't change it to Kelvin, you'll miss it. Easy way to miss a problem. How do I get from Celsius to Kelvin? Add 273 or 273.15. You want to get real picky about it, but just add 273, close enough. And that's how you change from Celsius to Kelvin. Make sure you change things to Kelvin. All right. Another thing I can measure is how much gas do I have. And so one way to measure that is the amount here in moles. Moles, remember, is how much do I have. And we're going to call that N. All right. And then the fourth thing that I can measure about a gas is its pressure. All right. Lots of units for pressure here. There's something called the atmosphere that we use quite often. The atmosphere is a really easy unit to conceptualize. It's basically how much air pressure you're feeling right now. 1 atmosphere is equal to the air pressure at sea level. You are actually a little bit above sea level. Midland's about 2,730 feet above sea level, roughly. I mean, different parts of the city, but that's about right. And so generally the higher up you go in elevation, the thinner the atmosphere is, and so therefore the less the pressure. But, it depends on altitude, but it also, especially down here, close to the surface, depends on weather. Sometimes you end up with high pressure systems that come through, warm air, and then you have cold air that comes in. Of course, those will have different densities. And so your what we call your barometric pressure, your air pressure changes from day to day. And then that's how they predict weather sometimes. But generally speaking, at sea level, 1 atmosphere. As you go up, it changes not a lot. At 2,700 feet, 0.98, probably, something like that. Maybe 0.985, maybe 0.99. Depends on the day. Some days it could be above 1. Who knows? But something along those lines. So it's about 1 here, but not quite 1. Okay? Well, The problem with the atmosphere is it's a really big unit. All right, so it's kind of like measuring the distance from here to the other side of the room in miles. You could do it, but it's probably not the best unit to be measuring from here to the other side of the room. It's a little bit too big. 1 atmosphere is equal to 14.7 pounds per square inch. Okay? In other words, for every square inch of your computer screen or phone, whatever you happen to be watching this on, there are 14.7 pounds of air pressure pushing on that screen. So why doesn't your screen break? Well, because on the other side, there's 14.7 pounds pushing the other way. And so they kind of equilibrate each other. See? But if you drew a vacuum, say for example, on the other side of your computer screen, what would happen to your computer screen? Well, it would break because that 14.7 pounds per every square inch on your screen, that's quite a bit of pressure. Would it explode? Well, no, it would actually break in because you're pushing from the outside and there's nothing pushing back on the inside there. Okay? And so, yeah, air pressure is a lot if you think about it. It's just that, you have a lot of air pressure pushing on you right now, but you've got air inside you pushing back. Let's say, for example, you go out in outer space where there is no air pressure around you. Well, now you've got air inside pushing out. There's nothing pushing in. What happens to you? Very, very bad things. I don't think I have to draw you a picture. So this is why you need spacesuit when you go out in outer space. You got to have something that equilibrates the pressure around you and also keeps you from getting fried by the sun there, or freeze-dried actually on the other side. But yeah, you can draw your own mental picture of what would happen there. But yeah, that's why you need a spacesuit when you go into outer space. There is, you got to have that pressure kind of equilibrate. So yeah, it's actually kind of big. It's just that you swim around in it all day. You don't really feel it. It's kind of like, does a fish ever feel like he's wet? Well, no, he just swims around in water all day. But yeah, it's 14.7 pounds per square inch, or PSI. You've probably seen that on a tire or something like that. All right. There's another unit here, by the way, called a bar, and then another unit called, which is a kilopascal essentially, and another unit called a pascal. Technically, the SI unit is the pascal, but we probably won't use that one. What we will use is we'll use atmospheres a lot. We'll also use this one over here, which is a little off screen. So let's get that over there. Okay. We'll use this millimeters of mercury. All right. And 1 atmosphere is equal to 760 millimeters of mercury. Now there's another unit here called a torr. And basically a torr and a millimeter of mercury are exactly the same thing. Are there very fine point? Yeah, there's a fine point difference there. But not really. Anytime you see millimeters of mercury or you see torr, those are interchangeable in this chapter. Don't worry about it. Okay, same thing. And 1 atmosphere is equal to 760 millimeters of mercury, or also equal to 760 torr. That is a conversion unit that would be given to you on a test. All right. So what's this millimeter stuff? I mean, that's not really a pressure unit. That's a distance unit, right? Where'd that come into play? Well, let's say, for example, here, I've got a U-shaped tube. It looks like this. Okay, and I've got some mercury maybe down here in the bottom. So I've got air pressure pushing on this mercury down here. Well, we know that liquids are incompressible, right? So imagine a tiny column of air, exactly the diameter of that tube, going all the way up into outer space. And you've got all that air pushing down on it. Which way does the mercury move? Well, it doesn't move. Why doesn't it move? Well, because you've got a tiny column of air over here on this side pushing down as well. And so the same pressure here, your mercury stays where it is. So, trick question. Okay? Well, just for fun, let's take this side over here and let's plug that up. And let's draw a vacuum over here. So there's no air over here. And we could either leave this open and use the atmosphere, or I can take a sample of gas here, and put it here. So now my gas is pushing on the mercury. There's nothing pushing back over here. Which way does the mercury move? Well, it moves this way, because see, liquids are incompressible. So all that force is going to make the mercury move up. Do you see that if I have a really high pressure over here, my mercury is going to move up quite a bit? If I have a very low pressure here, my mercury is going to move up just a little. Well, what I can do is I can measure how high that mercury goes up in millimeters, and that's a millimeter of mercury. So 1 millimeter of mercury is the pressure, air pressure or gas pressure, sufficient to push a column of mercury up 1 millimeter. All right, and that's a much smaller unit. So sometimes it's easier to measure things in a unit like this instead of a big one like this. This is like miles and this is like feet. Be an analogy there. Okay, but they're both units of measure of pressure, is what they are. All right, and of course a millimeter of mercury is the same as a torque. 1 atmosphere of air pressure is sufficient to push a column of mercury up 760 millimeters, or about 76 centimeters, or roughly 3/4 of a meter. Okay, which is pretty high if you think about it. All right. Again, your book has a nice little drawing here, so here we go. So here's our closed end, our vacuum here. Here's our gas. So here's our pressure. That pushes the mercury up, and your pressure of your gas is basically the height here. This density times G. You know, since we're using mercury here, yeah, it's just height. That's what it would be. So millimeters of mercury here. Okay. Here's the open end. See, if I've got open end now, I've got pressure pushing this way, and so here's my gas here. Okay. This measurement right here, this is called gauge pressure, by the way. There's two types of measurements. You can measure total pressure, or you can measure the gauge pressure. And gauge pressure is how much pressure do I have relative to the atmospheric pressure. So in this case, notice that the mercury actually went from here down. So what that tells me is my atmospheric pressure here is actually greater than my gas pressure here. So basically you measure that height and you subtract that height from 760, and that's what the pressure of the gas is. Over on this one, notice the mercury moved that way. That tells me that my gas pressure is greater than my atmospheric pressure. So essentially what you would do here is you would measure this height and you would add it to 760, and that would be the pressure of the gas. But if it's closed off over here, see, you just measure the height and that's it. Sometimes it's nice to know the total pressure or just the regular pressure. Sometimes the gauge pressure is nice. If you're measuring the pressure in a tire, you're measuring gauge pressure, because you know if your tire has a pressure of 1 atmosphere, you know that's not really going to get you anywhere because the pressure on the outside is 1 atmosphere. Your tire's not doing anything; it's just flat. But if your tire has a pressure of 2 atmospheres, we'll say inside it, total real pressure, then it's got a gauge pressure of 1 atmosphere. Say it's 1 atmosphere more than the air pressure on the outside. And of course you want your tires to have a greater pressure inside than the atmosphere. That's what makes them inflated. So yeah, there are cases where you want gauge pressure. There are cases when you want just regular pressure. And if you're an engineer, that comes into play. So I will toss that at you here. This is something called a manometer. And a manometer is a simple type of barometer. Okay? And a barometer is what we use to measure air pressure. So, for example, this is a barometer. So here's my little tube here. This is full of mercury. Here's my atmospheric pressure, which is pushing down. That causes the mercury to rise up in the tube. And for 1 atmosphere, it goes up 760 millimeters, or about 3/4 of a meter. So why am I using mercury here? Why don't I just put water in the barometer? I mean, it's cheaper, it's not poisonous, be easier to handle. Well, 1 atmosphere of pressure is sufficient to push a column of water up a tube 34 feet. So if you used water in a barometer, you'd have to have a barometer that was 34 feet tall. It would have to go outside and it would go right up the building. So we actually use mercury because the mercury doesn't go up so high, because it's so heavy. that the air can't push it up as high. And so now you've got a barometer that only needs to be about 1 meter high. See, it's more portable. So yeah, it's actually a good thing the mercury is heavy, because air pressure, like I say, is a lot. It's more than you think. You're just used to having it inside and outside, so you never have to worry so much about it. All right, makes sense? Okay, so that's pressure. The main units we'll probably use will be this millimeter mercury in torr and also atmospheres. We probably won't mess with pascals, although some books do. And PSI we may talk about just to kind of relate to something you've probably heard of before, but that's pretty much it. Okay? All right, well, I guess that's a good place to start. So we'll stop there. Now that we've got a bunch of variables that we can measure, is there any kind of relationship between them? Well, yes, there kind of is. And so that's what we're going to talk about next. We'll talk about the relation between the variables. We'll derive a bunch of equations you can use, because we know we really like to do math in here. And we'll go from there. Okay? So, I guess until next time, we will see you later, and we'll continue from there. So, bye.